In my last video, I looked at a simple pendulum and derived the equation for the period of a simple pendulum using the small angle approximation and the relationship between angular acceleration and angular displacement in simple harmonic motion. For this video, we will go back and look at a physical pendulum. And for our model of the physical pendulum, we will use a meter stick that's pivoted around a point and then allowed to oscillate freely on that pivot. We will need to know where its center of mass is and where the pivot is, and to be able to get the rotational inertia of the object that is oscillating. Remember that in a physical pendulum, the mass is spread out such that it is not concentrated all at the same point away from the pivot. The simple pendulum, what we have is a pivot, massless string, and all of the mass is concentrated at a point. In a physical pendulum, that mass is going to be spread out along the length of thing that is doing the oscillating. It is pinned at one point, and I've drawn my pivot not at the end point, but somewhere away from the end point, and it's also not at the middle. And then what we have is our center of mass that is, in the case of an ideal meter stick, is at the middle. But the center of mass of any given object might not be at the middle of your object. And we measure the distance between the pivot and the center of mass with h. And this object will have mass m and length L, and it will also have rotational inertia I. Sometimes you will be told the object's shape, and then you will find the rotational inertia, and sometimes you will simply be told it has a rotational inertia I. In this case, let's pretend that we know the rotational inertia around the center of mass, and we'll call that I center of mass. So this guy we will call I center of mass. Starting with the same place that we started last time, Newton's second law for rotation, we're going to look at this now physical object in exactly the same way with the forces as we did last time. We will displace it by an angle theta, and since this is the pivot, the angle theta is measured here. And our tension inside the object now, the tension points from the center of mass up to the pivot. The weight, also we can pretend that it acts at the center of mass. And it points straight down. And just like we did last time, this is the same diagram. All we've had to do is shift it to the center of mass of the extended object that we're looking at, and it's not in the middle of the pendulum bob. So let's use red here. The part of the weight that will make this object oscillate is still the sine piece, because what we have is two parallel lines, two vertical lines cut by a transverse. So this will be the same angle theta inside our triangle there. And we will go through the same first couple of steps are exactly the same as they were for the simple pendulum. We have an unbalanced force that's causing a twist and making this thing oscillate. And that unbalanced force is due to the weight that points perpendicular to the displacement of our pivot from the center of mass. So the left side of this equation is going to stay the same. It's the right side that's going to change, because what we don't have is all of the mass concentrated at a point. Now what we have is the mass is spread out. On the left side here, R cross F, still, R is now going to be how far is the center of mass displaced from the pivot. That's going to be H. The force is still going to be the mass times the gravity, but only the perpendicular piece, which is where the sine theta comes in. And once again, the torque is going to point towards equilibrium, so we need a minus sign. On the right side, this I is going to be the rotational inertia of our object when it's not pivoted around the center of mass. And you need to remember that that is from the parallel axis theorem. So this I is going to be I center of mass plus this adjustment term for the fact that it's not being pivoted around the center of mass. So on the right here, this will be I center of mass plus mh squared, and then we have alpha. Notice how we are now in the same position that we were in once we got down to this line, where we have to deal with the sine theta and the alpha. And we will deal with them in exactly the same way as we did last time. We will use the small angle approximation here to get rid of the sine, and we will use the relationship between alpha and theta in simple harmonic motion for kinematics as we did last time. So I will skip those derivations. They're in the previous video, and we will simply say small angle and SHM kinematics to allow us to make these substitutions. Having made those substitutions, that turns this rather ugly equation into this one. And it will allow us to get rid of the minus sign and a theta. And we will also, because what we want is the equation for the pendulum that relies on the period, not the angular frequency, because we want things that can be measured with meter sticks and stopwatches. And we will replace this with 2 pi over t, multiply both sides by t, take the square root because our omega is squared here. Doing a couple of steps of algebra, the 2 pi comes out of the square root. And what we get is this relationship here, in which we haven't been able to get rid of the rotational inertia of our object because we have an extended object and we don't know what its rotational inertia is yet. And what we have down here is mgh, which will look like potential energy. It's not really potential energy. It's the weight times how far did we move that weight away from the pivot, because we're not pivoting it around the center of mass. If we did pivot it around the center of mass, the thing wouldn't oscillate. It would just spin around a circle. Now the test for this equation is if I turn this physical object back into a simple pendulum, does this equation turn back into the simple pendulum equation? Let's try that. The rotational inertia of the center of mass of a point particle is 0. So if we collapse this meter stick down to all of the masses right here and it's a point particle, then this guy becomes 0. And what we have is mh squared, where h is going to be the length of the string. And down here on the bottom, that's going to be the mass of the meter stick that's been collapsed down to a point. And this h is also the length of the string. So this is going to be 0. These two masses then are going to cancel. One of these h's is going to cancel with this h, and we're going to left with one h on the top, which is the length of the string, and gravity on the bottom, which is exactly what we had before. For any of these sorts of equations, where you start out with a general principle, and then you make certain assumptions about the physical reality that you're dealing with. So one assumption is we're only doing small angles. Another assumption is because we're doing small angles, this will be simple harmonic motion. These assumptions are built into our equation. And that's how we end up with this equation that is usable, but you have to keep in mind that it's usable only under certain contexts. For example, this equation is slightly different because we made slightly different assumptions. We jumped straight to, we're assuming that we know the rotational inertia of this object is ml squared because it's a heavy mass on the end of an ideal massless string. And that's what gives us this equation. If you go back to the beginning of the first video, where we had two different things oscillating side by side, you should have seen that they oscillated with different periods. And they oscillated with different periods because those two physical objects have two different rotational inertias. Because of that, we're going to need to make different assumptions about how they will move, and that will lead to different equations. Any and all scientific equations have assumptions built into them that you will need to keep aware of as you use them so that you only use this equation in the appropriate context, or you use this equation in the appropriate context. Now, this one is more general, so it's more usable in more contexts because this equation boils down to this equation. But this one has already weeded out certain things that would still be allowed in this equation. So once again, what you need to be able to do is not just use this equation in the appropriate context, but you need to be able to start from the first principle of Newton's second law for rotation, which, by the way, has its own assumptions built into it. What we're assuming here is that the object itself will not be deformed. We have a rigid object that won't bend or flex or stretch. It's fixed. That's the assumption that's built into this equation here that we then carry all the way through to the end. You need to be able to start here, work all the way through. You're allowed to say small angle approximation and just do this. You don't need to rederive it from the Taylor series. And the same thing here. You're allowed to say simple harmonic motion kinematics and jump to here. You don't have to rederive it. But you have to be able to go all the way through this and end up here and then understand what this means and apply it to, let's now change it to a different shape. Instead of a stick, suppose that we make it a hoop that's pinned around the rim, or a disc that's pinned on the rim. Or how about a bowling ball that is suspended from a hook that's put in the thumb hole? You will need to know the rotational inertias of those specific shapes and how the rotational inertia changes when we move the pivot away from the center of mass and towards another point on the object.